In theory of elasticity, if we assume linear isotropic elastic material, two parameters emerge as the governing parameters. One was Young's modulus, and the other one Poisson's ratio. In terms of Hooke's law, generalized Hooke's law for 3D, the strain induced in the z direction is equal to 1 over E times the change in stress in the z direction minus Poisson, the change in stress in the x direction plus the change in stress in the y direction. You may remember that we also demonstrated that for small strains, epsilon volumetric is equal to epsilon 1 plus epsilon 2 plus epsilon 3. And we define Poisson's ratio as the strain in the normal direction to the stress in the parallel direction that we are considering for the loading direction. And because materials tend to get shorter and fatter, in other words, let's say contractive strains, in the other direction there will be strains in extension. One will be positive, the other one will be negative, and we like to establish material parameters, we define them in a positive sense. We are going to change the sign. So this is Poisson's ratio by definition. We can begin using these equations to make some predictions about Poisson's ratio. For example, if we are going to load in the z direction, and we could have called this epsilon z, epsilon x, epsilon y, this is going to be equal to epsilon z minus Poisson epsilon z, this is epsilon x, minus Poisson epsilon z for epsilon y. Therefore, epsilon volumetric is equal to epsilon z 1 minus 2 Poisson. Now, if there is no volumetric changes because the material has very high bulk stiffness, then epsilon volumetric equal to 0 means that, and we can multiply both sides by the inverse of epsilon z, means that 1 minus 2 Poisson is equal to 0. This is when epsilon volumetric is equal to 0, and Poisson is equal to 0.5. So this is the first limit that it is important for us to recognize, that when the material is incompressible, Poisson is going to be 0.5. How can we understand that? Well, imagine that I have a cube. When we squeeze it vertically, it's going to get shorter and wider, and the strain in each direction is going to be half. Why is that? Because we're not talking about just a square, we're talking about a cube, and so it will get wider in x and wider in y, which is what this equation is telling us. Therefore, any vertical contraction will manifest halfway in x and in y. Consequently, for incompressible materials, such as liquids, or at yield, in the case of many materials at yield, Poisson's ratio will approach 0.5. If we define the bulk modulus as the normal stress divided the volumetric strain, the normal stress in isotropic directions divided the volumetric strain, we need to add epsilon x, z plus x plus y. So I'm going to add 3 of them. And in all cases, the z, the x, and the y is going to be the isotropic stress. Then I will conclude that the bulk modulus is equal to Young's modulus divided by 3, 1 minus 2 Poisson. Therefore, 1 minus 2 Poisson is equal to E over 3 bulk modulus. Consequently, I can move to the left and to the right and then divide by 2. Poisson is equal to 1/2 minus E over 6 bulk modulus. This tells me that if Young's modulus and the bulk modulus are positive values, then Poisson's ratio will always be less than half. We are not going to have a Poisson's ratio greater than half if the material is a stable, elastic, isotropic material. With this in mind, now we can establish some ranges of Poisson's ratio. So far, we have established that Poisson's ratio can reach a value of 0.5. And let's establish here a value of 0, and let's see what that means. And 0.5 is when the medium is incompressible. Now, what does 0 mean? It means that when I shorten this element, when I squeeze it, it will get shorter, but it will not get wider. Now, there could be certain materials, and that would be very sensitive and collapsible soils, that when you squeeze them vertically, and of course there will be an isotropic state of stress or some lateral stress acting on them, the collapse could take place not only vertically but also allow the lateral stresses to squeeze in. So there is some possibility for negative Poisson ratio for highly collapsible soils. And when is it going to be incompressible? When this is liquids, saturated soils under undrained conditions. Basically here we are assuming that the bulk stiffness of the water and the mineral that makes the grains is infinitely high, which is actually not true. So even water will have a Poisson's ratio 0.49, 0.495. If that wasn't the case, the P wave velocity would go to infinite. That means that if this is incompressible, in this direction, and the volume remains constant, in this direction is contraction. Now, what about dilative soils? Well, dilative soils would plot in this direction, but as we established before, that wouldn't satisfy linear elasticity anymore because it would give us negative Young's modulus or bulk modulus. But in reality, dilation is possible, but not in linear elasticity. So once again, this is, if we are in that regime, we are violating linear elastic material. So now we have to think, where else do we stand here for our soils? So let's consider the case of small strain, for example, wave propagation, or really small strain loading processes. And that would be, for example, a simple cubic packing. And in a simple cubic packing, when I loaded all the deformation under small strains, which is the range of linear elasticity, all the deformation takes place primarily at the contacts. And on the equatorial plane, there is very little shortening, and if there is very little shortening, there is very little expansion. And so in a simple cubic packing where all the deformation takes place at the contact and there is very little deformation on the equatorial plane where the transverse contact takes place, there is virtually no lateral strain. So in a simple cubic packing, Poisson's ratio is equal to 0. Now I could also take other materials like a body-centered cubic. Poisson's ratio is equal to the Poisson's ratio of the mineral that makes the grains divided 2 times 3 minus 2 Poisson's ratio of the mineral that makes the grain. Now, if you think of the Poisson's ratio of the minerals being about 0.3, you will realize that this number is very small. Therefore, for all small strain processes, under drained conditions, now we conclude that Poisson's ratio is somewhere between 0 and about 0.15. If you analyze P and S wave velocities for a unsaturated soil, highly unsaturated, therefore the liquid is not affecting the wave propagation, so preferably, let's say, for a dry soil, the ratio of the P and S wave velocities is related to Poisson's ratio, and you will see that the Poisson's ratio is actually a very small value for small strain processes. So in this regime is the regime of drain, small strain. So what happens now when we push theory of elasticity a little bit for the range that is relevant for example, settlement computations? If that's the case now, we have to think of a different situation. Like, for example, if a soil was in a dense packing and it was in this type of configuration, when I squeeze the soil and it contracts, vertically contracts, there will be a lateral expansion that will determine the Poisson's ratio due to fabric changes. And we have to be very careful because now we are pushing theory of elasticity at the point where we are exceeding the elastic threshold strain that we computed earlier. And so now we can be in pretty much the whole regime. In conclusion, Poisson's ratio reflects, number one, strain regime, strain level under drained conditions. If it is undrained, Poisson's ratio goes to pretty much 0.5, so undrained, saturated. And if we are going to push it a little bit further, it will also be affected by the fabric. In general, to assume a priori that Poisson's ratio is 0.3 is probably premature, and we have to be more careful in how we analyze our data, because in soils, Poisson's ratio could be even slightly smaller than 0. For sure, it can reach 0.5, and it can be in a wide range. Most importantly, if we do field characterization or laboratory characterization with P and S wave velocities, the Poisson's ratio of the skeleton tends to be very small.